China just built a chip that wasn't supposed to exist for another 5 years. Silicon Valley called it impossible. The Dutch said it would take decades. American sanctions were designed to prevent exactly this. But in a lab in Shenzhen, engineers proved everyone spectacularly wrong. What happens when the world's most powerful export controls backfire? When the news broke in April 2025, the initial reaction was disbelief. Then came the panic. Chinese researchers had published findings in Nature, one of the world's most prestigious scientific journals, detailing a functional 1 nanometer microprocessor. To put that in perspective, Taiwan's TSMC, the undisputed leader in semiconductor manufacturing, won't attempt mass production of 1 nanometer chips until 2030. Samsung is struggling just to make 2 nanometer technology profitable. And yet here was China, supposedly years behind, claiming they'd already crossed the finish line. But before we declare technological warfare won or lost, we need to understand what actually happened. Because the reality is far more nuanced, considerably more strategic, and infinitely more consequential than any headline could capture. The chip in question carries a poetic name, Wuji. Developed by professors Xiaopeng and Bao Wanjing at Fudan University, this 32-bit RISC-V microprocessor represents something genuinely groundbreaking in materials science. Unlike every processor currently running your devices, which rely on traditional silicon, Wuji is constructed from molybdenum disulfide, a two-dimensional material measuring exactly 1 atom in thickness. The processor contains approximately 5,900 transistors and measures less than 1 nanometer thick. That physical measurement is where the explosive claim originates, and from a purely technical standpoint, it's accurate. But context matters enormously here. In 2017, researchers at Vienna University of Technology created the previous record holder for two-dimensional material chips, a modest 115 transistor device. Jumping from 115 to 5,900 transistors represents legitimate scientific progress, the kind that earns recognition in peer-reviewed journals and advances our understanding of quantum-scale engineering. The same Fudan team also developed a flash memory chip called Phoenix that writes data in 400 picoseconds, translating to roughly 25 billion operations per second. In controlled laboratory conditions, they achieved a 94.3% yield rate, meaning almost all the chips they fabricated actually worked. These are real accomplishments by any scientific standard. But here's where the narrative diverges sharply from reality. The smartphone in your pocket right now contains between 15 and 20 billion transistors. Modern commercial processors operate at scales that dwarf Wuji by factors of millions. There's an enormous chasm between a 5,900 transistor research prototype and chips that actually power our digital civilization. The real battleground. While university labs chase scientific milestones, the genuine competition unfolds in massive fabrication facilities where billions of dollars change hands and millions of chips flow off production lines monthly. TSMC began mass-producing 2 nanometer chips in the latter half of 2025. Their yield rates exceed 60%, which represents exceptional performance for bleeding-edge technology. They've implemented gate-all-around transistor architecture for the first time at commercial scale, and major clients including Apple, NVIDIA, and AMD have already committed billions to secure supply. Samsung launched 2 nanometer production simultaneously, but faces severe challenges. Their yields languish around 40%. At the 3 nanometer level, Samsung achieves only 50% success rates, while TSMC delivers 90%. That 40 percentage point gap translates directly into wasted silicon, higher manufacturing costs, and dissatisfied customers. According to TSMC's public roadmap, 1.4 nanometer technology won't arrive until 2028 at the earliest. True 1 nanometer mass production remains scheduled for 2030. Achieving that milestone requires extreme ultraviolet lithography machines from ASML, a Dutch company that operates as the sole source for this critical technology. Each EUV machine costs upward of $150 million. Some sources cite figures approaching $400 million, and contains over 100,000 precision components sourced from 800 suppliers spanning 5 continents. These are the most complex machines humanity has ever constructed, and China cannot buy them. American pressure ensured that when sanctions landed in 2019, ASML was explicitly prohibited from selling EUV technology to Chinese customers. This was supposed to be the technological choke point that would prevent China from ever competing in advanced semiconductors. Then something unexpected happened. September 2023. Huawei releases the Mate 60 Pro smartphone, and immediately analysts worldwide begin tearing it apart. What they found inside, well, it really shook the foundations of American export control policy. The phone's processor, called the Kirin 9000S, was confirmed as a genuine 7-nanometer chip manufactured by SMIC, China's leading semiconductor producer. This shouldn't have been remotely possible. SMIC doesn't have ASML's EUV machines. Instead, SMIC accomplished what Western analysts insisted was technically infeasible. They used older deep ultraviolet lithography equipment and a technique called multi-patterning. Rather than printing circuit patterns once using advanced EUV light, they print the same pattern repeatedly, 34 separate exposures compared to 9 with EUV technology. It works, but, inefficiently. SMIC's 7-nanometer chips cost 40 to 50% more than equivalent TSMC products. Yield rates fall below 50%. For 5-nanometer chips currently under development, yields could drop to 30 or 40%. By conventional business logic, these economics are catastrophic. But China isn't operating under conventional business constraints. The government maintains something called the National Integrated Circuit Industry Investment Fund. In March 2023 alone, they injected $1.9 billion into Yangtze Memory Technologies. SMIC's total capital expenditure reached $7.47 billion in 2023, up 17.6% year over year. This isn't a company chasing quarterly earnings reports. This is a nation-state executing a decades-long strategic plan where financial losses are acceptable costs as long as technological capability advances. By 2025, Chinese fabrication facilities controlled over 25% of global capacity for mature node foundries. Monthly wafer production capacity hit 7.6 million units, representing 25.6% of worldwide semiconductor manufacturing capability. Then came March 2025, and the real shock. Photographs surfaced from inside a Huawei facility in Dongguan showing equipment that, according to Western intelligence assessments, just shouldn't exist. China appears to have constructed a working EUV machine using completely different technological principles. While ASML uses massive lasers to blast tin droplets into plasma, the Chinese approach vaporizes tin between electrodes and converts it to plasma through high-voltage electrical discharge. Different engineering path, identical result. The 13.5 nanometer wavelength light necessary to etch microscopic circuits. The Chinese EUV project, honestly, reads like industrial espionage fiction. Former ASML engineers were recruited through aggressive talent acquisition campaigns launched in 2019. Signing bonuses ranged from 3 to 5 million yuan, roughly $420,000 to $700,000, plus housing subsidies. Workers operated under false identities inside classified facilities. Among the key figures is Lin Nan, formerly ASML's head of light source technology. Lin spent over 5 years in ASML research before returning to China in April 2021. His team filed 8 patents on EUV light sources in just 18 months. In December 2024, Lin's team published research demonstrating 3.42% conversion efficiency in generating EUV light, actually exceeding the 3.22% achieved by the Advanced Research Center for Nanolithography in the Netherlands. ASML acknowledged the intellectual property theft in its 2022 annual report, stating they experienced unauthorized misappropriation of data relating to proprietary technology by a former employee in China. The project operates under China's Central Science and Technology Commission, led by Ding Xuexiang, a close ally of President Xi Jinping. Huawei plays the central coordinating role, linking state research institutes with private sector partners. Sources describe it as China's Manhattan Project for semiconductors, involving thousands of engineers working in coordinated cells. The explicit goal is to produce advanced chips on machines that are entirely China-made, completely eliminating reliance on American-controlled supply chains. The analog revolution, huh? October 2025 brought another shock. A research team at Peking University published findings in Nature Electronics that, honestly, made every chip engineer in Silicon Valley pause. They'd built an analog computing chip using resistive random access memory that processes calculations 1,000 times faster than NVIDIA's H100 GPU, while consuming 100 times less power. The kicker? They built it using older 7-nanometer manufacturing technology that, well, the United States never bothered sanctioning. Jensen Huang, CEO of NVIDIA, saw this coming. At the Financial Times AI Summit in London, he said something nobody expected. China is going to win the AI race. Not might win, will win. For the past century, we've been doing computing inefficiently. Every computer operates on digital computing, information broken into ones and zeros. Your processor performs calculations in one physical location, while data sits in memory somewhere else. Every operation requires data to travel back and forth. This is called the von Neumann bottleneck, and it's why your laptop generates heat and why training large AI models consumes more electricity than small towns use in a month. Before digital computing dominated, engineers experimented with analog computers using continuous electrical signals. For certain mathematics, analog computers were faster than early digital machines. But they had one fatal flaw. They couldn't maintain precision. Electrical noise and temperature changes meant calculations would degrade into nonsense. That precision problem is what Chinese researchers just solved. Their chip uses resistive random access memory cells that store information as different resistance levels. Each memory cell can hold hundreds of different resistance values. When you need to perform a calculation, the chip doesn't move data anywhere. The memory cell itself becomes the processor. The Peking University team achieved 5 orders of magnitude improvement in analog precision, 100,000 times more accurate than any analog computer previously built. The results: 1,000 times the throughput of an NVIDIA H100, 100 times better energy efficiency, accuracy equal to 24-bit fixed-point digital systems. They manufactured this chip using commercial production processes that exist right now in Chinese fabrication facilities. The sanctions paradox. Since 2022, the United States has blocked China from purchasing advanced GPUs. The entire strategy assumed that without cutting-edge American chips, China couldn't keep pace in artificial intelligence. But, sanctions backfire. When you deny someone technology, you don't make them surrender. You make them innovate around you. While American companies spent billions refining digital GPU architecture, Chinese researchers asked a fundamentally different question. What if we don't need digital chips at all? Energy is the real battleground. Training GPT-4 required computational power equivalent to running thousands of high-end gaming PCs continuously for months. NVIDIA's latest GPUs consume 700 watts and require massive cooling systems. An analog chip delivering similar performance while using 7 watts instead of 700 watts doesn't just save money, it fundamentally transforms what's possible. China has structural advantages rarely discussed. Their government provides electricity subsidies that can reduce power costs by 50%. They're building AI-ready power infrastructure specifically designed for high-performance computing. Applications are already obvious. Next-generation 6G networks need to process signals from hundreds of antennas simultaneously. Analog chips can manage massive parallel signal processing while using minimal power. Smartphones could run sophisticated AI locally without cloud connections. Military drones could fly longer and process battlefield intelligence faster. Silicon Valley currently has no response. NVIDIA's roadmap contains more digital GPUs, with more transistors consuming more power. Nobody in America has a major program developing analog computing at scale. Chinese researchers are already working on next-generation versions. They're targeting deployment in telecommunications first, then AI training centers, then defense applications. And the timeline isn't some distant future. It's 2 to 3 years. The Rare Earth Weapon. December 1st, 2025. China deployed a strategic weapon that could reshape the semiconductor industry. New regulations on rare earth minerals now require that any lithography equipment containing at least 0.1% of these Chinese materials must obtain an export license. This move ensures China controls its strategic resources while directly impacting Dutch companies like ASML. The context traces back to September 30th, when the Netherlands intervened in Nexperia, a Chinese semiconductor company. Amsterdam removed the Chinese CEO and transferred 99% of shares to an independent trust without warning. For China, this was perceived as politically coordinated action with the United States. A critical factor: most of Nexperia's actual production, over 70%, is located in China. Following Dutch intervention, Beijing retaliated by blocking exports of power semiconductors to Europe. Production at Chinese plants fell from 90% capacity to below 10%. Industrial impact was immediate. In Germany, Volkswagen and BMW factories slowed production, incurring millions in daily losses. Within 2 weeks, Europe lost over $3.5 billion in production value. The most direct strategic blow hit ASML. Dutch lithography machines rely heavily on Chinese rare earths. Essential components have no viable alternatives outside China. Replacement attempts increased costs by 40% and reduced performance by 30%. China controls roughly 90% of global rare earth refining capacity. ASML's stock experienced a 15% single-day plunge in October 2024, its largest drop since 1998. The company now expects China to represent approximately 20% of total revenue in 2026, down from 49% in mid-2024. The strategy America pursued may have backfired spectacularly. By cutting off access to Western technology, the U.S. created exactly what it feared most: a competitor forced to innovate independently who no longer needs Western permission to advance. China didn't beat ASML at their own game. They changed the game entirely. A century ago, we abandoned analog computing because we couldn't solve the precision problem. China just proved we gave up too soon. The question now isn't whether China will achieve EUV independence or analog computing dominance. The question is, how fast, and what happens to the global semiconductor industry when they do? October 2025 might be the moment historians point to when explaining how technological leadership shifted. Not through superior products, but through superior strategy. Not by playing the game better, but by refusing to play it at all. Sanctions don't stop innovation. They redirect it. And sometimes what emerges on the other side is more dangerous than what you tried to prevent. The chip war nobody saw coming isn't being fought on the terms anyone expected. And right now, China is holding cards nobody knew existed.